we're not done with inclined planes. I'm inclined to tell you more. We've dealt with the inclined plane free to move on a smooth horizontal surface, and we've obtained the acceleration of the inclined plane with a particle of mass small m coming down, falling down, sliding down the inclined plane. No friction anywhere, so far smooth. But we've dealt with the same thing in a few ways, but I'm going to now deal with the inclined plane with the frame of reference or the observer being the inclined plane itself. That means we're going to solve the problem in a non-inertial frame. The inclined plane is an accelerated frame, and we're going to solve this problem in the inclined plane. As we have seen before, the inclined plane has an acceleration a to the left, courtesy n sine theta. We've done this so many times. So n sine theta is ma. So now look at small m. We're going to look at small m in the inclined plane frame of reference. So in the inclined plane frame of reference, which is a non-inertial frame, if I have to apply Newton's second law, then what I need to do is, to the set of real forces n and mg, I need to add a force minus m times the acceleration vector of the inclined plane. So, which is very clearly small ma to the right is the pseudo force acting on the inclined plane, right? So then, together with n, ma and mg, real and pseudo forces coming together, conniving, cementing together. And what would that produce? That would not give me the acceleration in the ground frame. That is going to give me the acceleration small a of the particle in the inclined plane frame of reference, which we already know is along the plane, right? So that means the resultant of all these forces, n, ma and mg, is going to be an acceleration a down the plane. This is what will happen, right? That being the basic idea. I could have written my equations of motion for small m parallel to the plane and perpendicular to the plane, or I could have written that in the vertical direction and in the horizontal direction. So if I choose to deal with directions parallel to the plane and perpendicular to the plane, then what I have is, parallel to the plane, set of real and pseudo forces is going to be ma cos theta plus mg sin theta, ma cos theta plus mg sin theta, right? And perpendicular to the plane is going to be, as you can see, n plus ma sin theta, n plus ma sin theta, which is this, n plus ma sin theta, and there is mg cos theta like this, right? Now, there is, so these forces will give me what? Relative acceleration. But relative acceleration of small m perpendicular to the plane has to be 0, keeping in mind the wedge constraint, keeping in mind the condition so that small m maintains contact with capital M. So net of all forces in this direction has to be 0, because there is no relative acceleration in this direction. So very clearly, n plus ma sin theta must just about balance mg cos theta, right? That's as far as this is concerned. And in this direction, what do? They produce an acceleration small a. So then we have, along the plane, we have the equation of motion as mg sin theta plus ma cos theta as small m into a. Right. So using these two equations once again, along with, of course, n sin theta equal to na, this remains cardinal all the time. Using this equation, and this equation, I can once again solve for capital A, n, and small a. Capital A, like before, will turn out to be mg sin theta cos theta by capital M plus small m sin square theta. Similarly, small a will turn out to be capital M plus small m g sin theta divided by capital M plus small m sin square theta. That is what is going to happen. So, and you know, I could have solved the same problem by resolving my real and pseudo forces horizontally and vertically. In the horizontal direction, I clearly have ma plus n sin theta, ma plus n sin theta. In the vertical direction, I have mg and n cos theta. And what do? Look, the acceleration in the inclined plane frame of reference is small a, which has a horizontal component, as you can see, a cos theta, and has a vertical component, a sin theta. Who's instrumental in producing a cos theta? ma plus n sine theta, right? Ma plus n sine theta results in ma cos theta, right? Right? The real plus zero forces give me what? Relative acceleration. So relative acceleration in this direction is a cos theta, in this direction is a sine theta. In this direction, who causes relative acceleration a cos theta? Ma plus n sine theta. In the vertical direction, what's the equation of motion? Mg minus n cos theta equals m into a sine theta, a sine theta, a sine theta. So then I have this equation along with this equation, n sine theta is capital M into A, giving me the values of capital A and small a. So we've learned in a certain sense how to deal with this problem in the ground framework, in the inclined plane framework, and by resolving forces parallel and perpendicular to the plane, as well as resolving forces vertically in the direction of Mother Earth and horizontally perpendicular to the direction of Mother Earth. So I'm assuming that you're getting a hang of things and that you're feeling comfortable with it. But I'm still not done. I'm still not done. I'm going to demonstrate yet another concluding aspect of the same thing. They are all cosmetically different. They deep within, they converge somewhere. But I will demonstrate another way of handling this problem so that it gives you mental comfort dealing with these situations. Thank you so much. Bye.